I first saw the bell tower on a cold afternoon in February, standing at the corner of Södermälarstrand, Stockholm, where official records place its construction in 1892. I had come to review a minor restoration file, just a set of routine maintenance notes from 1978, but an image tucked between two pages stopped me. It was an 1893 photograph from the Municipal Archive showing the tower during its first winter. What unsettled me was not the bell itself, but a perfectly circular hydraulic aperture beneath the base, something no Victorian engineer in Sweden was documented using at the time. When I visited the site, the aperture was gone, sealed by concrete poured decades later. Yet the stone surrounding it, granite blocks cut with uncanny symmetry, showed machining traces far cleaner than anything a late 19th century crew could produce. Some researchers would call such features Tartarian signatures. I simply noted the discomfort and kept walking. The official documents claim that construction of the small bell tower began in April 1892, supervised by municipal architect Axel Kumlien. His journals describe a modest structure meant to coordinate river traffic along the southern quay. The project budget was unremarkable, 8,400 kroner, standard for municipal infrastructure of the period. The construction crew numbered 12 men. The timeline projected completion within 5 months. Nothing about the project suggests anything exceptional. Kumlien's preliminary sketches, filed in March 1892, show a simple octagonal tower rising 9.2 meters above the waterline. The foundation plan indicates standard masonry techniques, granite blocks set in lime mortar, depth not exceeding 1.4 meters. The bell housing, a timber frame with copper cladding, was designed to accommodate a bell no larger than 1.2 meters in diameter, weighing approximately 850 kilograms. Yet the earliest photograph, dated January 1893 and stamped with the Municipal Archives catalogue number F2847, reveals a bell far larger than the tower's proportions would justify. I measured the image against the known height of the doorway visible in the frame. The bell's diameter exceeds 1.8 meters, perhaps approaching 1.85. Its weight, based on standard bronze casting densities of the period, would have been closer to 2,200 kilograms. The tower's timber frame could not have supported such mass without catastrophic failure. Even more unusual is the stone plinth beneath the bell. In the photograph, it appears to be carved from a single block of granite, roughly 2.1 meters in diameter. The surface shows an unnatural smoothness, no chisel marks, no scoring patterns, typical of 19th century Swedish stonework. The block sits perfectly level despite the quay's documented slope of 1.8 degrees toward the water. While examining the 1978 renovation folder, a manila envelope containing 17 pages of typed reports and 3 hand-drawn diagrams, I found a handwritten note from surveyor Lars Bergstrom, dated June 14, 1978. Sub-level cavity under plinth extends farther than expected. Cylindrical shape, approx. 2.8 meter depth. Walls remarkably smooth. Recommend sealing to prevent structural instability. Such cavities are common in older structures, typically the result of erosion or settling, but Bergstrom's description, cylindrical, uniform with smooth walls, suggested intentional excavation or construction. The dimensions he recorded matched almost exactly the profile of sub-level chambers I had seen documented beneath structures in Kazan and Pskov, chambers that fringe researchers classify as Tartarian hydraulic reservoirs. I told myself it was coincidence. Stockholm's bedrock is granite. Circular excavations are not impossible. But as I left the archive that evening, the winter sun already set. The image of that impossible machining lingered, the plinth's perfect levelness, the bell's inexplicable size, the sub-level cavity extending deeper than any foundation plan justified. A quiet question formed, one I couldn't ignore. What had the 1892 construction crew actually built, and what had they merely inherited? Later that week, I returned to Söder-Mälarstrand on a grey Thursday morning. The tower, reconstructed in the 1960s after storm damage in February 1958, was said to follow the original blueprints on file at the City Engineering Office. The reconstruction supervisor, according to a brief newspaper article from May 1960, had praised the quality of the original drawings, calling them remarkably precise for their era. Yet when I compared the current brick pattern on the lower wall with an 1894 engineering drawing, Blueprint Series K, Document 247, signed by Assistant Engineer Frederick Lindholm, I noticed a discrepancy that stopped me cold. The original design included a circular opening, exactly 42 centimeters in diameter, positioned 68 centimeters above the waterline, and aligned with perfect geometric precision to the plinth's center line. In the present structure, that opening exists only as a faint outline beneath a coat of concrete, poured sometime between 1961 and 1963, according to a notation I found in a maintenance log. I returned the following day with a laser measuring device borrowed from a colleague in the surveying department. The curvature of the surviving original stone, 3 blocks that had escaped replacement during the 1960s reconstruction, yielded readings that defied my expectations. The radius was precise within 0.5 millimeters across a full meter of arc. I took 16 measurements at different points. The variance never exceeded 0.4 millimeters. Swedish industrial tools of the 1890s, the lathes, the grinding wheels, the cutting equipment available to municipal construction crews, could not achieve tolerances that tight, certainly not in granite, and absolutely not on site in the uncontrolled conditions of a quayside construction zone. Modern CNC machinery can produce such precision. Victorian-era hand tools and steam-powered equipment cannot. The contradiction sat before me, measured and undeniable. A folded map, tucked inside the same blueprint folder, drew my attention. It depicted older districts of Stockholm with faint labels from an earlier century, streets that had been renamed, buildings long demolished. In the decorative margin, rendered in flowing script, appeared the words Great Tartary. At first it seemed irrelevant, a mere cartographic flourish from an age when mapmakers filled empty spaces with speculative geography. But then I examined the map's legend more carefully. Among the symbols denoting churches, mills, and fortifications, I found a circular mark, 2 concentric rings with a small dot at the center. The notation beside it read, hydraulic aperture, diameter 42 centimeters. The exact diameter I had just documented. I checked the map's date, 1847, 45 years before Kumlian's tower was supposedly built. A routine site check was beginning to drift into something else. The precision was wrong. The map was wrong. The sealed opening aligned too perfectly with something documented half a century before official construction. I felt the shift quietly, like the change in pressure before snow, a sense that the ground beneath the accepted narrative was less solid than anyone had assumed. The municipal records identify the stone supplier as a quarry near Västanfors, approximately 180 kilometers northwest of Stockholm, active from 1867 to 1904. I contacted the Regional Historical Society and obtained samples of quarry documentation. Granite blocks from that site were characterized in period reports as coarse-grained, uneven in color, and notoriously difficult to shape. The quarry specialized in rough-cut foundation stones and paving blocks, not precision architectural elements. Contemporary quarry records from 1891-1893 list deliveries to Stockholm. 847 blocks in June 1891, 1,203 blocks in September 1892, none matching the specifications of the bell tower plinth. The largest documented delivery measured 1.4 meters in maximum dimension. The plinth is 2.1 meters across. Yet the plinth beneath the bell tower displays a polish closer to machine-lathed surfaces than hand-tooled masonry. I examined it in morning light, late afternoon shadow, and under portable LED illumination at night. The surface shows no visible tool marks, none, not the parallel scoring of bush hammers, not the dimpled texture of point chisels, not the subtle undulations that even skilled masons leave behind. The granite appears to have been ground and polished to a mirror finish, then weathered naturally over decades. I found a photograph from 1895 taken by engineer Niels Ekstrom on May 3rd during his documentation of spring flood damage along the southern waterfront. The image, catalogued as EKS 1895-037 in the Royal Engineering Society archive, shows the bell tower as an incidental background detail. Ekstrom's focus was the damaged embankment 30 meters to the west, but in the lower right quadrant of the photograph, beneath pooled floodwater that reflects the tower's base, one can see a pattern of radial grooves etched into the foundation stones. I had the photograph digitally scanned at high resolution, 4800 dpi, and examined the enhanced image. The grooves form a spiral configuration, 7 distinct channels radiating from a central point and curving outward in a logarithmic pattern. Each channel measures approximately 8 centimeters wide and appears to be cut to a depth of 3 to 4 centimeters. Modern researchers associate such patterns with hydraulic pressure regulation systems, channels designed to distribute water flow evenly from a central source, preventing erosion and managing subsurface pressure. These features appear repeatedly in structures that alternative historians label Tartarian infrastructure. Ekstrom's journal contains a brief remark dated May 4, 1895, the day after he took the photograph. Substructure beneath tower shows channels of unknown purpose, not included in original plan. Queried site foreman, he claimed ignorance of their function. Channels appear older than surrounding construction. Either Cumlian added undocumented features during construction, a violation of municipal contracting procedures that would have been noted in budget reviews, or the construction crew built atop something older, something already present when they broke ground in April 1892. I stood at the site that evening, wind cutting through the quay, the water dark and restless below. The replacement stones installed during the 1960s reconstruction looked crude compared to the originals visible in Ekstrom's photograph, blocky, uneven, their surfaces rough. Something had been removed, deliberately or otherwise, leaving behind a silence I could almost feel under my feet. The spiral channels were gone, filled with concrete. But the photograph remained, and in that image the evidence of something unexplained persisted like a whisper beneath the official narrative. City archives list the bell as removed for preservation in 1924, filed under Municipal Order M 1924-0847, dated October 12th. The notation is brief. Bell removed from Södermälarstrand Tower for museum preservation due to historical significance and structural concerns. Yet no museum in Stockholm claims to hold it. I contacted the Nordic Museum, the City Museum, the Royal Armoury, the Maritime Museum, and 3 private historical societies. None had records of acquisition. The bell's disappearance is simply noted in a 1926 inventory update with a single line. Disposition undocumented. I found a renovation document from 1937, a typed report, 17 pages, prepared by construction foreman Gustav Andersson, describing the emptying of the tower's substructure in preparation for foundation reinforcement. Page 11 contains a paragraph that arrested my attention. Lower chamber accessed via trapdoor in floor. Chamber contains metal brackets of unusual design, inconsistent with tower's presumed function as signal post. Brackets appear designed to suspend or anchor object of significant weight. No historical documentation found explaining their presence. items catalogued and discarded per Municipal Directive 37 K089. Metal brackets. I returned to the 1892 engineering drawings. Cumlian's plans show the bell suspended from a simple timber crossbeam, supported by iron bolts at 4 points, standard church bell mounting, no specialized brackets, no metal anchoring system in the sub-level chamber. The engineering drawing includes no sub-level chamber at all. When I compared the documented dimensions, I realized the original bell was heavier than the tower could reasonably support. Using the diameter visible in the 1893 photograph, approximately 1.8 meters, and assuming standard bronze composition, 78% copper, 22% tin, density 8.8 g samtsem throbai, the bell would have weighed between 2,100 and 2,300 kilograms. Cumlian's timber frame, according to material specifications in the construction log, consisted of pine beams 18 centimeters square. Structural engineering tables from the period indicate such beams could support approximately 1,200 kilograms before risking failure. The bell exceeded the tower's capacity by nearly double. Standing inside the current tower, access granted through a municipal maintenance contact, I noticed an irregularity in the floor that the 1960s reconstruction had not fully obscured. A faint circular indentation approximately 8 millimeters deep marked the exact geometric center of the floor space. I measured its diameter, 1.82 meters. The bell's footprint preserved in the wood like a shadow. That diameter matched the footprint of bells found in churches across regions once labeled Tartaria on 18th century maps, bells famed for their size, their unusual acoustic properties, and their mysterious casting methods. In Kazan, a bell of nearly identical dimensions had been documented before its removal in 1889. In Pskov, another, removed in 1901. In Irkutsk, one more, dismantled in 1907. All bells of exceptional size, all undocumented in foundry records, all removed during modernization campaigns. Victorian Sweden had no foundry capable of producing a bell of that scale and purity in 1892. The largest Swedish bell foundry, located in Lund, specialized in church bells up to 1.2 meters in diameter. Larger bells were imported from Belgium or Germany, and those imports were meticulously documented in customs records. I searched the Swedish customs archive for 1891-1893. No bell exceeding 1.5 meters in diameter appears in the import ledgers. Yet one was here, photographed, measured, removed, and now it is gone. I closed the file and felt a subtle constriction in my chest, not fear, but the pressure of accumulating evidence that refuses to align, a bell that should not exist, a tower that could not support it, brackets designed for unknown purposes catalogued and destroyed, and beneath it all a circular indentation in wood marking the ghost of something that official records cannot explain. I began assembling every surviving image of the Södermälarstrand bell tower from the decade following its official completion in 1892. The municipal archive retained 6 photographs, catalogued under reference codes beginning with SMT, Södermälarstrand Tower. Private collections, accessed through historical societies and family estates, held 3 more. Together they provided a timeline the documents never offered, a visual record that contradicted the official construction narrative at almost every point. A photograph dated October 1894, taken by railway surveyor Johan Mellgren during documentation of the new Southern Railway spur, shows the tower at dusk. Mellgren's notation on the reverse reads, "Light insufficient for track documentation, captured tower by chance while testing exposure time." The bell, still present then, clearly visible in the frame, reflects the last light along its bronze surface with unusual brightness. The metal appears polished, almost luminous. But what drew my attention was the shadow cast beneath the structure. The sun, setting behind the photographer at approximately 18 degrees above the horizon based on the season and time, Mellgren noted 6:20 p.m. on the reverse, cast a long shadow toward the east. Shadow revealed a subterranean recess far deeper than the foundation plan allows. I calculated the cavity depth using shadow trigonometry, with the sun at 18 degrees elevation and the shadow extending 7.3 meters from the tower's base, measured against the visible cobblestones in the photograph, each stone approximately 12 centimeters across. The subsurface void extended at least 2.4 meters below ground level. Cumlian's foundation plan specified a depth of 1.2 meters. The discrepancy, double the documented depth, suggested either massive settlement or the presence of a pre-existing chamber that the 1892 construction had not created, but merely built atop. Then there was the stone alignment. In the oldest images, particularly a photograph from July 1893 showing dock workers unloading timber near the tower, the foundation block courses form a radial pattern converging at the exact center beneath the bell. I counted 17 courses visible above the waterline, each row oriented with geometric precision toward the central point. That pattern is not present today. The 1960s reconstruction used conventional horizontal coursing, standard for the period. But before the 1937 renovation, before the wartime modifications, before the slow accumulation of repairs and patches, the geometry was immaculate. Concentric rings of stone, mathematically proportioned, converging with astronomical precision. This is not typical 19th century key construction. Victorian engineers built functionally, not geometrically. The radial pattern served no structural purpose for a simple signal tower. The same formation appears in structures that alternative researchers classify as Tartarian hydraulic nodes, often beneath domes or towers in cities that appear on pre-1800 maps labeled Tartaria. The radial stonework allegedly facilitated water distribution or pressure equalization, though mainstream historians dismiss such claims as speculative. I am not asserting equivalence, only noting that the geometry matches. The pattern is identical. In Mellgren's notebook, a leather-bound journal I discovered in his grandson's estate, donated to the Railway Museum in 2003, he wrote a single curious line on October 17, 1894. Returned to tower site to verify earlier observations. Stones too perfect, unlike the mason's work nearby. Curvature and alignment exceed craft standards I have witnessed elsewhere. Consulted with stonemason Larson, he expressed equal puzzlement. That discrepancy lingered with me, whispering beneath the photographs like a second narrative running parallel to the official record. The document said one thing: tower built in 1892, standard construction, simple purpose. The photograph said another: precision beyond the era's capabilities, geometric sophistication inconsistent with function, and a sub-level infrastructure that appeared in no plan but showed clearly in shadows and stone. When I examined the engineering drawings dated February 1892, signed by Cumlian and the city engineer Eric Moberg, I expected inconsistencies typical of the period, measurements rounded to convenient fractions, slight variations between plan and execution, the normal drift that occurs when paper meets stone. Instead, I found precision that exceeded even modern tolerances. The radial measurements, distances from the central point to 17 marked positions around the foundation perimeter, were exact to tenths of a millimeter. In 1892, with hand drafting tools, the cross-sections showed curves that would be nearly impossible to carve manually. Parabolic arcs with mathematical consistency, junction points calculated to 6 significant figures. One dimension, the radius of the sublevel chamber, was noted as 1.473 meters, not 1.4 meters, not 1.42 meters, but 1.4173, a precision implying measurement instruments that did not exist in Victorian Sweden. Yet when I compared the drawings to current measurements taken with a laser total station, borrowed from the city's surveying department with official permission, something became clear. The tower that stands today is subtly misaligned. The center line of the current structure, measured from the geometric center of the foundation to the apex of the roof, deviates by approximately 1.3 degrees from the orientation shown in the original drawings. No renovation document mentions such a shift, not the 1937 foundation work, not the 1958 storm repairs, not the 1960s reconstruction. Yet the deviation is measurable, consistent, and, when I plotted the original alignment on a site map, clearly deliberate. The 1892 orientation aligned the tower's central axis with the waterline at a specific angle, 73.4 degrees from magnetic north, which in 1892 corresponded to approximately 77 degrees from true north, accounting for period magnetic declination. Why would Victorian engineers specify such precise alignment for a simple signal tower? The drawings imply the original alignment was deliberate, optimizing the tower's geometry with the water level below. But for what purpose? Hydraulic regulation, acoustic amplification, signal transmission? I could not say. The documents offered no explanation. Mowbray's construction log from May 1892, a bound ledger with daily entries in precise handwriting, contains an unusual entry dated May 17th. Sub-foundation discovered during excavation, circular cavity already present at depth 1.8 meter. Stone walls, smooth, purpose unknown, debated with Kumlian whether to fill or incorporate. Decision: incorporate into design. Adjustments to plan required. Incorporate. Victorian engineers seldom incorporated unknown cavities into their designs. Standard practice dictated filling anomalous voids with rubble or concrete, ensuring structural stability and predictable behavior. Yet the design appears built around this pre-existing cavity, as though the architects deferred to whatever lay below, treating it not as an obstacle to overcome, but as a feature to preserve. This concession, professionals adapting plans to pre-existing geometry, mirrors patterns seen in buildings across territories formerly labelled Tartaria on 18th century maps. In Kazan, the construction log for a municipal building, 1887, notes, "Foundation adjusted to accommodate existing stone chamber." In Skov, renovation records 1896 describe preservation of sublevel infrastructure of uncertain origin. In Tobolsk, engineers in 1883 documented incorporation of pre-existing hydraulic features into new design. Structures reshaped around inherited foundations again and again across thousands of kilometers. Was this tower another example? I couldn't draw a conclusion with certainty, but the tension between drawing and reality asked questions I wasn't prepared to answer. The precision was too high, the alignment too deliberate. The adaptation to pre-existing infrastructure too convenient. And beneath it all, the quiet acknowledgement in Mowbray's ledger that something was there before them, something they chose not to destroy but to incorporate, to build around, to preserve, in silence. 2 weeks into the investigation, I uncovered a set of municipal maintenance reports from 1903 to 1911, filed in a water-stained folder marked Key Infrastructure Southern District. Most concern routine inspections, checking mortar joints, documenting water damage, recording seasonal flooding patterns. The reports are perfunctory, written in bureaucratic shorthand, but a single line in the 1907 report, dated March 22nd, captured my attention and refused to let go. Lower chamber inaccessible due to standing water, metallic resonance heard when probing with iron rod. Chamber walls appear to be lined with metal plates, purpose uncertain. No maintenance action taken, recommend professional assessment. Metallic resonance implies hollowness, an interior cavity lined with metal plates rather than solid stone or brick. Such construction is utterly inconsistent with the tower's official purpose as a simple signal post for coordinating river traffic. Why would a maritime signal tower require a metal-lined sub-level chamber? The official explanation, if one existed, would have appeared in the maintenance records. Yet the follow-up report from 1908 makes no mention of the chamber, the resonance, or any professional assessment. The observation simply disappears from the administrative record, but the chamber itself matches components found beneath Eastern European bell structures associated by fringe researchers with supposed Tartarian pressure systems, chambers allegedly designed to regulate hydraulic pressure, store water, or serve some acoustic purpose that mainstream archaeology does not acknowledge. A photograph from 1908, catalogued in the National Archives under reference code NAF 1908-2847, shows workers draining a flooded section of the quay approximately 40 meters west of the bell tower. The image quality is poor, early glass plate negative, exposure uncertain, but in the background, partially submerged in standing water, is a circular iron ring embedded in the foundation stones. The ring measures approximately 38 centimeters in diameter based on comparison with visible cobblestones. It disappears from later photographs. The 1960s reconstruction photos show smooth stone where the ring once was. The ring resembles those found in star-shaped fortifications across regions once labeled as Tartary, rings used allegedly for hydraulic control or mechanical anchoring of gates, pumps, or pressure release mechanisms. I had documented similar rings during earlier research, one in the Gdansk fortress wall, diameter 36 symmetry, another in the Kazan Kremlin foundation, diameter 39 symmetry, a third in Pskov's city wall, diameter 37 symmetry, all dating from the 17th to early 19th centuries. To avoid drifting into speculation, I compared the geometry directly using high-resolution scans and measurement overlays. The Stockholm ring's diameter aligns within 3 centimeters of the Kazan ring. The mounting position, 38 centimeters below the documented waterline in 1908, matches the positioning of the Pskov ring relative to the river Velikaya. The metal composition, based on visible corrosion patterns in the photograph, appears to be wrought iron with possible bronze alloy elements, consistent with the Gdansk ring analyzed in a 1987 metallurgical study. Officially, these are independent traditions, Swedish maritime infrastructure having no connection to Russian fortress engineering, which in turn has no connection to Polish defensive architecture. Each ring in the conventional narrative represents a separate solution to separate problems in separate contexts, but architecture is rarely coincidental at that level of precision. Identical diameters, identical positioning relative to water levels, identical material composition, identical association with sub-level chambers and hydraulic systems. The probability of independent invention producing such exact correspondence across thousands of kilometers strains credibility. I stood at the site the following evening, watching the water lap against the stones, the evening light turning the harbor copper and gold. I knew the ring was long removed, cut away during some forgotten renovation, discarded or melted down. Yet I felt as though something beneath the surface remained, silent, sealed, waiting. The metal-lined chamber still existed below, filled with concrete perhaps, but not destroyed, buried, not erased, and in that burial a kind of preservation. Curiosity drove me deeper into Stockholm's archives, into the sub-basement levels where older records mouldered in climate-controlled darkness. The bell removed in 1924 remained unaccounted for, absent from every museum inventory, missing from every collection catalogue. So I sought any mention of bells of similar size cast in the region during the late 19th century, searching through foundry records, metallurgical society journals, and industrial manufacturing logs. Nothing. Swedish foundries of that decade specialized in much smaller church bells, none exceeding 1.2 meters in diameter. The largest producer, Bergholz and Sons in Lund, maintained meticulous casting records. I reviewed their ledgers from 1889 to 1895, 47 bells produced, largest diameter 1.18 meters, heaviest weight 890 kilograms. The 1.8-meter Söder-Mälarstrand bell, captured clearly in Mellgren's 1894 image, has no casting record, no transport log, no metallurgical entry in any Swedish industrial journal I could locate. In the Nordic Metallurgy Bulletin 1893, Volume 8, Issue 3, I found a brief note referencing bell alloys in an article by metallurgist Dr. Anders Ostrom. No casting of exceptional scale undertaken this year. Moulds for bells exceeding 1.2 meters diameter absent from regional foundries. Import of large bells from continental producers continues to supply ecclesiastical demand. Yet the tower's bell existed in photographs, multiple photographs, from multiple angles, measured, described, documented in renovation orders. And in a 1912 renovation order, municipal document R 1912-0334, filed under Tower Maintenance, Southern District, one line stood out. Bell of unknown provenance to be removed carefully. Weight exceeds expected measure by significant margin. Special rigging required. Exceeds expected measure. The bell weighed more than the structure could support, as though it had been placed atop a foundation specifically designed to bear its mass, but not built by the crew who erected the visible tower in 1892. The foundation predated the tower. The bell predated the tower. The Victorian construction project merely assembled visible components atop infrastructure that was already there. This mirrors patterns I've documented in other cities: bells too large for their housings, towers seemingly retrofitted around them, foundations older than official records acknowledge. In Kazan, records describe a bell of uncertain manufacture, removed in 1889. In Irkutsk, a bell exceeding local casting capabilities, dismantled in 1907. In Harbin, a bell origin undocumented, relocated in 1913, all oversized, all unexplained, all removed during modernization campaigns. Some alternative historians classify these as Tartarian resonance devices, bells allegedly designed not merely for signaling but for some acoustic or vibrational purpose that conventional archaeology does not recognize. I do not endorse that claim, but I can no longer ignore it as an interpretive framework. The pattern is too consistent, the anomalies too numerous, the silence too coordinated. When I read the renovation order again, late at night, in the archives reading room, I noticed a faint smudge beside one line, as if the writer hesitated before finishing the note. Ink pooled slightly where the pen had paused. That hesitation echoed my own, the reluctance to state clearly what the evidence suggested, the professional caution that prevents conclusions without proof, the quiet awareness that something was wrong with the accepted narrative. What kind of bell appears in photographs, fits no industrial record, exceeds the capacity of its structure, and vanishes without explanation? What kind of bell requires special rigging for removal, yet has no documented installation? What kind of bell exists for 32 years before being removed to a destination that no institution claims? The 1937 renovation files were fragile, yellowed, brittle, stamped with moisture rings, but the diagrams inside were startlingly clear. A cross-section drawing of the bell tower foundation included something no earlier blueprint mentioned: a lower chamber, circular, nearly 3 meters in diameter. The foreman labeled it simply "existing cavity," no origin listed. Existing, not constructed, not excavated, existing. When I visited the site with a small laser rangefinder and scanned the tower floor through an access hatch, the reading confirmed the chamber shape, a round void directly beneath the plinth, depth approximately 2.4 meters, walls remarkably smooth. Smooth stone at that depth rarely survives without weathering, unless it was originally quarried and fitted with extraordinary precision. The curvature matched sub-level cavities beneath structures across Eastern Europe. Cavities, alternative researchers argue, are remnants of Tartarian hydraulic pressure systems. I don't claim that, but the geometry is undeniably similar. A margin note in the 1937 file read, "Metal plates removed, purpose uncertain." Metal plates beneath a 19th century stone bell tower make no sense, yet their removal was documented and then forgotten, as though an anomaly had briefly surfaced and been buried again. I left the archive that evening unsettled, caught between documented fact and architectural impossibility. Axel Kumlian, credited with designing the tower, kept meticulous records from 1867 to 1901. Yet, in the year of the bell tower's construction, his journals show an unusual gap. Between March and September 1892, not a single entry. Before the gap, his writing is typical: notes on timber orders, drafts of facades, weather complaints. After it, he resumes discussing unrelated projects. The bell tower appears only twice. May 12th, foundation presented complications. September 3rd, project finalized, though not to my preference. Complications is vague, but paired with Maubay's earlier remark, sub-foundation discovered, it suggests the crew encountered something unexpected below the site. A set of unpublished letters held in a private collection contain a line attributed to Maubay. "We are not building so much as adjusting to what is here." Adjusting. That single word aligns with dozens of buildings I've studied across regions once labelled Tartary on 17th century maps, structures aligned to sublevels, retrofitted around pre-existing geometry. In those cases, official narratives frame the inherited components as natural formations or unknown earlier works. Here, Stockholm's tower was simply built, silently absorbing its predecessor's footprint. I ran a fingertip along the edge of a blueprint and felt the paper's slight curve, an unintended echo of the chamber beneath the tower. I wondered what Kumlian and Maubay had seen, and why they wrote so little. As my investigation broadened, I compared the tower's measurements with architectural sites far beyond Sweden. In Kazan, a bell removed in 1889 had a diameter nearly identical to the Södermälarstrand bell, 1.79 meters, yet no casting record exists there either. In Gdansk, renovation files from 1904 describe the discovery of a circular substructure beneath a small riverside tower, again with smooth curvature inconsistent with local tools of the period. And in Tbilisi, a decommissioned bell tower photographed in 1891 shows a foundation pattern nearly identical to Stockholm's original radial layout. These locations share no cultural lineage, no common architect, no documented exchange of engineering techniques. What they do share is presence on earlier maps: Mercator's 1595 atlas, Sanson's 1683 chart, Bowen's 1747 world map, all labeling vast regions under the name Tartaria. Mainstream historians argue these labels were geographic abstractions, not civilizational markers. Yet the architectural parallels remain: identical foundation radii, similar hydraulic cavities, bells too large for their structures, and a tendency for these components to be removed or buried during modernization. I retrieved a 1901 photograph of the Stockholm Tower's base, now stored in a private maritime archive. The image reveals a faint spiral groove pattern, barely visible, encircling the plinth. The same motif appears in Pskov, Ufa, Irkutsk, and Harbin. Coincidence is possible, but identical spirals, identical radii, identical missing bells. The silence of the official record grows louder the more doors I open. By the time I returned to the Södermälarstrand Tower with the full archive assembled, I understood more about what was missing than what remained. The 1937 renovation removed the metal plates, and the 1924 removal discarded the bell. The 1960s reconstruction poured over the aperture. Later, maintenance filled the spiral grooves with mortar. Each change was documented individually, mundane, administrative, justified on its own. But when placed together, they formed a pattern more revealing than any single act, a systematic dismantling of components whose origins no one claimed. The most striking file was an internal memo from the Municipal Facilities Board, 1959. Lower substructure is anomalous relative to city inventory. Recommend consolidation and discontinuation. Anomalous. The tone was bureaucratic, but the implication was unmistakable. The workers recognized the chamber did not match any known municipal design, yet instead of investigation, they opted for neutralization. Structures across Eurasia once associated, fairly or not, with so-called Tartarian systems show similar trajectories in their records: sublevels filled, bells removed, hydraulic conduits sealed. Officially, these were safety measures, efficiency measures, modernization measures. Individually they make sense, collectively they read differently, quietly subtracting the same types of elements in city after city, decade after decade. Standing inside the tower on a grey autumn morning, I pressed my hand against the interior wall. The stones felt colder here than elsewhere, as though the sealed chamber beneath still held a temperature of its own. A place that once resonated, now silenced. I returned to the archive one final time, intent on closing the investigation. Yet closure proved elusive. A fragile envelope contained the earliest known photograph of the bell before installation, labeled simply 1892, unloaded at key. The bell sits on a wooden pallet, towering over 3 workers. Its shape is unmistakable: elongated shoulders, unusually thick lip, flawless curvature. This form is seen repeatedly in bells attributed, sometimes speculatively, to supposed Tartarian manufacture: oversized, acoustically refined, compositionally pure. Their foundries are undocumented, their transport unexplained. The Stockholm bell resembles one photographed in Kazan in 1887, another in Irkutsk in 1890, another in Harbin in 1892. No trade route connected these sites, no industrial record lists simultaneous fabrication, yet the bells exist in photographs, then vanish in renovation logs. The final renovation file for Stockholm, dated 1978, contains a single understated line: residual components disposed, sublevel filled. Residual components not identified, not catalogued, disposed. The tower today stands quiet, inert, stripped of whatever once lay beneath it. But the stones hold memory, radial scars softened by mortar, symmetry out of place for the century that claimed to create them, and a void beneath my feet, measured, documented, sealed, whose origin remains unassigned. When I close the last folder, the contradiction stays with me. How a simple bell tower, supposedly built in 1892, could contain design choices older than its architects, cavities not in its plans, and a bell that exceeded the capabilities of its era. Across thousands of kilometers, structures of similar form carry echoes of the same asymmetry between official record and physical reality. Some call these echoes Tartarian, I call them unresolved. In a faded 1894 photograph taken at dusk by Johan Mellgren, the bell tower stands newly built against the darkening sky. At the base, barely visible in the original glass plate negative, more apparent in modern digital enhancement, a circular aperture catches a glint of light before darkness hides it. The aperture measures 42 centimeters across. Its edges show the same impossible precision I measured in the surviving stones. The aperture is sealed now, filled with concrete poured in 1961, but the photograph remains in the archive catalogue number SMT 1894017, preserved in acid-free sleeves, waiting for anyone who cares to look. And in that silent ring of stone, beneath layers of modern concrete and Victorian brick, the unanswered questions continue to rest, unmoved, unacknowledged, and patiently waiting beneath the weight of the years.